methods for applied mathematics. And the last few classes we completed Fourier transform definition and correspondingly properties problems here. And similarly, infinite Fourier sine and cosine transform. That's also called FFST, FFCT, IFST, IFCT or FST, Fourier sine or cosine transform. Correspondingly, we have seen some problems and properties and problems. Today move on to finite Fourier cosine transform. Finite Fourier cosine transform and finite Fourier sine transform. So far, you consider the range of the function is minus infinity to infinity for Fourier transform and 0 to infinity for Fourier sine transform and Fourier cosine transform here. Cosine transform. Now, if you consider a finite range here, 0, L, a finite range 0, L, 0, pi, 0, 2, 0, 4, then in that range, the function is continuous here. And how can you determine the Fourier transform here? How can you determine the Fourier transform? That is very simple from the definition of Fourier series, half-range Fourier series idea. Simple from the help of the definition of half-range Fourier series idea definitions here, and we will see that definition once again here, right, one by one. Yes, just now I completed this idea in the for another section, and just I will recall that ideas here once again. Put the heading as finite Fourier sine and cosine transform. Finite Fourier sine and cosine transform. Put the heading as finite Fourier sine and cosine transform. Finite Fourier sine and cosine transform. That another simplified version is FFST and FFCT. FFST and FFCT. FFST and FFCT. Right there. FFST, finite Fourier sine transform. Finite Fourier sine transform. If f of x is continuous over the range 0, L, f of x is continuous over the range 0, L, f of x is continuous over the range 0, L, 0, L, then the finite Fourier sine transform, then the finite Fourier sine transform, finite Fourier sine transform is given by FSR f of x. FSR f of x is equal to FSR f of x is equal to integral 0 to L f of x sin n by x by L, integral 0 to L f of x sin n by x by L, and the result will be, after substituting the limits for x here, result will be a function of n, fs of n, fs of n, fs of n, fs of n. This definition came from the idea for half-range Fourier series. You know that half-range Fourier series, you see the right side here, half-range Fourier series, sine series is f of x equal to 2 by L, f of x is equal to summation bn sin n by x by L, not 2 by L, bn sin n by x by L, where bn is what? Bn is 2 by L, 0 to L, f of x sin n by x by L dx. For bn equal to 2 by L, bn equal to 2 by L, integral 0 to L f of x sin n by x by L dx, f of x sin n by x by L dx. That one we can consider. But this integration 0 to L f of x sin n by x by L, that will be considered as a finite Fourier sine transform. The Fourier series in the Bn, integration comes here. That integration taken as a finite Fourier sine transform. Because the Fourier transform comes in terms of the integral idea. So that integral taken as a finite Fourier sine transform. where f of x, if you want to identify from this f of x, if you want to identify inverse, this is the f of x here. But you are removing 2 by L here in the integral, you are removing that 2 by L. For that 2 by L, you have to multiply here because Bn contains 2 by L of so on. Bn contains 2 by L. That 2 by L you are missing here, therefore you have to multiply this 2 by L here, not 2 by L here. Therefore that integral only you can have. Therefore 2 by L summation Bn sin n by x by L. Therefore that part considers the inverse finite Fourier sine transform. Okay, that is here. Okay, 2 by L summation n equal to 1 to infinity. You are approximating that f of x in terms of Fourier series, the help of Fourier series. Not exactly the function with the help of Fourier series, right? And the inverse finite Fourier sine transform, and the inverse finite Fourier sine transform is given by, and the inverse finite Fourier sine transform is given by f of x equal to 2 by L, 2 by L summation n equal to 1 to infinity, summation n equal to 1 to infinity fs of n sin n by x by L, fs of n sin n by x by L, fs of n sin n by x by L. Right. Similarly, cosine transform, cosine series, finite for half range cosine series. From that you can write half range cosine series means you can write a naught by 2. Fourier series is a naught by 2 plus a n cos n by x by L. A n is what? 2 by L 0 to L f of x cos n by x by L. The same thing you can apply. That 0 to L, you are removing that 2 by L, therefore 0 to L f of x cos n by x by L dx, that will be considered as a fc of n, Fourier cosine transform, Fourier cosine, right? Finite Fourier cosine transform, FFCT, finite Fourier cosine transform. Put that in as FCI f of x, FCI f of x is equal to 0 to L, 0 to L f of x cos n by x by L dx, 0 to L f of x cos n by x by L dx. 0 to L f of x cos n by x by L dx, that is equal to fc of n, and the inverse finite Fourier cosine transform is given by, and the inverse finite Fourier cosine transform is given by, and the inverse finite Fourier cosine transform is given by f of x equal to, a naught by 2, okay, the Fourier series a naught by 2 can get, instead of a naught fc of 0 by 2, if you put by 2, that 2 by L is you have to multiply, because you are removing this 2 by L here, we have to multiply 2 by L, that 2 get cancelled, 2 get cancelled, therefore you can write 1 by L here, 1 by L fc of 0, 1 by L fc of 0 plus 2 by L summation n equal to 1 to infinity, n equal to 1 to infinity fc of n cos n by x by L, fc of n cos n by x by L. Okay. You are not considering that 2 get cancelled, therefore you can write 1 by L fc of 0 plus 2 by L summation n equal to 1 to infinity fc of n cos n by x by L. The above two definitions, put a note in the above definitions, if we replace L equal to pi, a, 4, etc., a particular values, L equal to particular values, pi, a, 4, etc., we get FFST and FFCT, finite Fourier cosine sine transform and finite Fourier cosine transform in certain intervals, 0 comma pi, 0 comma a, 0 comma 4, etc. This is generally 0 comma l. Particular values you can get particular intervals here, 0 comma pi, 0 comma a, 0 comma 4, etc. Okay. Now take some problems based on these definitions here. Find the finite Fourier cosine transform of e power minus ax, sorry, e power ax. Find the finite Fourier cosine transform of e power ax in the interval 0 comma pi. 0 comma pi. Find the finite Fourier cosine transform e power ax in the interval 0 comma. Solution: given the function f of x equal to e power ax, f of x equal to e power ax in the interval 0 comma pi, f of x equal to e power ax in the interval 0 comma pi. We know that we are asking finite Fourier cosine transform. Finite Fourier cosine transform in the interval 0 comma l. General interval you know that again. In the interval 0 comma l is fc of f of x, fc of f of x. That is equal to 0 to l. 0 to l f of x cos n by x by l dx. F of x cos n by x by l dx. But they are asking in the interval 0 comma pi. For in 0 comma pi, 0 comma pi, you replace l equal to pi. L equal to pi. fc of f of x is equal to fc of f of x is equal to 0 to pi, interval 0 to pi, f of x cos nx dx. Interval 0 to pi, f of x cos nx dx. Since l equal to pi. So replace f of x equal to e power ax. F of x equal to e power ax. Over 0 to pi, interval 0 to pi, e power ax cos nx dx. E power ax cos nx dx. fc of e power ax equal to interval 0 to pi, e power ax cos nx. Now integrate this one, e power ax by a square plus n square. A cos nx plus n sin nx. A cos bx plus b sin bx form here. Therefore, a cos nx plus b n sin nx. 0 to pi. 0 to Substitute the limits here, x equal to pi, e power a pi a square plus n square. A square plus n square. Substitute here a cos n pi plus n sin n pi. Apply 0 here, e power 0 1 by a square plus n square. Cos 0 1 for a, sin 0 0 plus 0. Looking at e power a pi by a square plus n square. Cos n pi, everyone know that cos n pi is minus 1 whole power n, sin n pi is 0. Sin n pi is 0. Cos n pi is minus 1 whole power n. Over a into minus 1 whole power n plus 0. A into minus 1 whole power n plus 0. Minus a by a square plus n square. So minus a by a square plus n square. Here is also a by a square plus n square. Here is also a by a square plus n square. Therefore, we can take it outside here. Outside. a by a square plus n square of e power a pi. Here you see that e power a pi minus 1 all power n. This is minus 1. E power a pi minus 1 all power n minus 1. This is Fourier cosine transform of f of x. This is Fourier cosine transform of f of equal to e power ax. Find Fourier cosine. The same way, can you give the answer for this one here? Second problem. Find the finite Fourier sine transform of finite Fourier sine transform of f of x equal to x square. Find the finite Fourier sine transform of f of x equal to x square in the interval 0, L. In the interval 0, L. They are asking finite Fourier sine transform. Sine transform. Therefore, by definition, FSI f of x sine transform FSI f of x is equal to finite Fourier 0 to L integral 0 to L f of x sin n by x by L dx. Integral 0 to L f of x sin n by x by L dx. Sin n by x by L dx. For FSI x square they are asking here. For 0 to L f of x is x square sin n by x by L dx. Then integrate by Bernoulli's formula uv product of two functions here uv formula. Oh, right. U is x square. V1 means integration of sin n by x by L. That will be minus cos n by x by L by n pi by L. Cos n by x by L by n pi by L minus differentiation of this one is 2x. And here integration of this one is already a minus is there, therefore sin n by x by L and one more n pi by L n square pi square by L square. This is formula minus plus differentiation of this one 2 integration of this one. Already a minus is present, sin is minus, therefore minus plus cos n by x by L by one more n pi by L n cube by cube by n cube. Then formula minus plus differentiation of this one 0. Then 0 to L. Limit is 0 to L. Therefore, now limit is for x. Therefore, we take the terms without x outside. So here minus L pi n pi, take it outside here. X square cos n by x by L. Because if you write like this here, it will be you cannot miss any minus sign or plus sign, and also I can remove the unnecessary terms here. X square cos n by x by L 0 to L. Here constant values are minus plus 2 L square by n square pi square. Okay. 2 L square by n square pi square. This is plus 2 L square by n square pi square. And here sin n by x by L 0 to L.
Sir, in the second term, x is there now, sir. 2xl square now.
X is the x is x. Okay. And third term 2L cube by n cube pi cube. 2L cube by n cube pi cube. Cos n by x by L 0 to L. Go on. Right now, substitute the limits here. When apply L here, L square, here L get cancelled. Cos n pi is minus 1 whole power n. When apply 0, 0 here because x is comes 0 here. Minus L pi n pi, L square minus 1 whole power n minus 0. First limit is L square x square minus cos n pi is minus 1 whole power n minus 0 minus L pi. Second term is second term is when apply L here, L get cancelled here, sin n pi 0. When apply 0, sin 0 is also 0. Here is also 0 here. Here plus 2 L square by n square pi square 0 0 here. Plus 2 L square by n square pi square 0 0. Third term 2 L cube by n cube pi cube. And apply L here, cos n pi minus 1 whole power n, cos 0 minus 1. 2 L cube by n cube pi cube, cos n pi minus 1 whole power n, cos 0 1 minus 1. For FSR x square, FSR x square, here multiply minus L cube by n pi, minus L cube by n pi minus 1 whole power n, multiply. And this is totally 0. Here 2 L cube by n cube pi cube, minus 1 whole power n minus 1. This is Fs of n. This is Fourier sine transform of x square. Fourier sine transform of x square. Okay. Now we see some problems using inverse finite Fourier sine transform. Okay? Inverse finite Fourier sine. Third problem. Find the function f of x. Find the function f of x. Find the function f of x if its finite Fourier sine transform is, if its finite Fourier sine transform is Fs of p, Fs of p is equal to 1 minus cos p by p square pi, 1 minus cos p by p square pi, 0 less than x less than pi, x range is 0 to pi, and p values are 1 2 3 etc. 1 2 3. Generally we can use the notation FFST for its finite Fourier sine transform means Fs of n, okay, Fs of n. But instead of Fs of n, they have given that Fs of p, Fs of p. Therefore, instead of n, they have given that p. Or we can change it as n, no problem. N takes a value 1 2 3, p takes a value 1 2 3. We can change, no problem here. Therefore, here Fs of n equal to 1 minus cos n pi by p square by cos n pi is minus 1 whole power n. N value is 1. FFST is given. From this, you have to identify f of x by inverse. Given FFST is given FFST is Fs of n Fs of n is equal to 1 minus cos n pi by n square pi, 0 less than x less than pi, n equal to 1 2 3 etc. Fs of n is equal to 1 minus 1 whole power n by n square pi. Therefore, by inverse finite Fourier sine transform, we have inverse finite Fourier sine transform, we have f of x equal to 2 pi L summation n equal to 1 to infinity Fs of n into sin n by x by L. Fs of n into sin n by x by L. You know inverse for finite Fourier sine transform, that is approximated by f of x approximated by Fourier series here. 2 by L summation n equal to 1 to infinity Fs of n sin n by x by L. This is L equal to pi. Here L equal to pi because x varies from 0 to pi. For L equal to pi here. For replace L equal to pi here, for f of x can be written as 2 pi pi summation n equal to 1 to infinity Fs of n sin n x. Okay. For f of x equal to 2 pi pi summation n equal to 1 to substitute Fs of n, that is 1 minus minus 1 all power n squared pi. 1 minus n minus 1 all power n square pi sin n x. This is for using the inverse finite Fourier sine transform. Okay, inverse finite Fourier sine transform. Similarly, we have the another problem. Find the function f of x. Find the function f of x if it's finite Fourier cosine transform. Finite Fourier cosine transform is given by fc of n equal to sin n pi by 2, n equal to 1, 2, 3, etc. fc of n is equal to sin n pi by 2, n equal to 1, 2, 3, etc. For n equal to 0, it is pi by 4. N equal to 0, pi by 4. 0 less than x less than pi. Okay? Right. You know, fc of n is given, f of x you have to identify. Therefore, f of x, you can give the answer. F of x equal to solution is 1 by L, fc of 0, 2 by L, summation n equal to 1 to infinity fc of n cos n by x by L. You know the definition. Inverse finite Fourier cosine transform. But here L equal to pi. L varies from x varies from 0 to pi. Therefore, L equal to pi. You can substitute and we will give the answer. Can you give the answer here? L equal to pi 1 by pi fc of 0, 2 pi pi fc of n cos nx. L equal to pi 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 can cancel nx. fc of 0 is this one, n equal to 0. N equal to 1, 2, 3, you can use sin pi by 2. Pi by 4, this pi pi can cancel 1 by 4 plus 2 pi pi, n equal to 1 to infinity. fc of n is sin n pi by 2 cos nx. Sin n pi by 2 cos nx. Okay, this is your answer. Is that problem over?
Sir,
Hmm. Okay. Okay. These are all some ideas of Fourier transform, finite Fourier cosine transform and sine transform. You can use directly the definition here. And we have completed the concepts of Fourier transform. Fourier transform is minus infinity to plus infinity, and then 0 to infinity means finite Fourier sine transform and finite Fourier cosine transform. Finite Fourier sine and finite Fourier cosine transform, that is 0 to infinity here. And further, but finite interval means finite Fourier sine transform 0 comma L, 0 comma L, finite Fourier sine transform and finite Fourier cosine transform. Finite Fourier cosine. Further, you have to use the boundary value problems using sine and cosine transform, and the solution to one-dimensional heat equation problems, heat conduction problems. These are all application problems here, and that we have to discuss further here. And before that, I will give some additional problems in the Fourier transform, Fourier sine and cosine transform, and finite Fourier cosine transform. Finite Fourier cosine transform, you can note it down here. I take it as a assignment number 2. And before that, I will also discuss some ideas in the Fourier uh, transform ideas here. Generally, we consider the function f of x. We consider the function f of x or f of t. F of x or f of t. That function, generally we consider that function is called function or pulse. Function or pulse in the time domain. Function or pulse or signal in the time domain. In that manner we can consider it. Therefore, these things are called f of x or f of t are generally called function or pulse or signal in the time domain. In the time domain here. Correspondingly, if you are finding the Fourier transform, Fourier transform, that is termed as a f of s. That is termed as a f of s. They are also called function or pulse in the frequency domain. Function or pulse in the frequency domain. This f of s that obtained transformed result is called function or pulse in the frequency domain. Frequency domain. That thing you have to remember. That thing you have to remember. Therefore, instead of asking find the Fourier transform, find the Fourier transform, they may also ask like that here. Find the uh, function in the frequency domain. Find the function in the frequency domain means Fourier transform here. Fourier transform. In that manner, we can consider again. Similarly, reconstruct the pulse in the time domain. Reconstruct the pulse in the time domain means it will be treated as a inverse Fourier transform. Inverse Fourier transform. In that manner, we can consider. For that thing, you can remember. You can remember. And also, in the Fourier transform, we can think that total energy carried by a signal, total energy carried by a signal, f of t, is termed as integral 0 to infinity mod f of t square dt, the Parseval's identity. In the range 0 to infinity means you can consider like this here, but minus infinity to infinity means you can consider minus infinity to infinity. In that manner, you can consider. Integral 0 to infinity mod f of t square dt, integral 0 to infinity mod f of square dt, depends upon is cosine transform or sine transform. That thing you can consider. Total energy carried by signal. It is also called power spectrum of a signal. It is also called power spectrum of a signal of the signal f of power spectrum of the signal f of t. That is also we can consider. Well, that Parseval's identity tells us that total energy carried by a signal in the range, respective range that you can consider. Okay. And this is not low pass filter here, that we have to change it. Some standard function in the Fourier transform we can remember. Some standard function in the Fourier transform we can remember. First one is rectangular rectangular wave function that is termed as f of x equal to 1 for mod x less than a and 0 for mod x greater than a. Mod x. This is also called low pass filter function. Low pass filter function. That is also called. And then triangular wave function. Triangular wave function that will be represented by a minus mod x less than a and 0 for mod x greater than a. This is triangular wave function. These things you can remember. These things. Triangular wave function here. That things you can remember. Remember. These two things you can remember. Right. About total energy carried by signal is this partial certainty and function or pulse or signal in the time domain, that is original function. Its transformed function is called function or pulse in the frequency domain. Therefore, that's also we can remember. Yes. Now we take assignment problem here.
Sir,
Assignment
one
number
minute.
2.
On the rectangular wave function and other cartoon, sir, on the slide.
There are rectangular wave function and triangular wave function.
Thank you, sir.
Okay.
சார் ரெக்டாங்குலர் வேவ் ஃபங்க்ஷன் மாதிரி ட்ரையாங்குலர் வேவ் ஃபங்க்ஷனுக்கு ஏதாவது நேம் இருக்கா சார்?
Triangular wave function வந்து இல்லை செப்பரேட் ஒன்றும் இல்லை, செப்பரேட்டாக நேம் இல்லை.
ஓகே சார், தேங்க்யூ சார்.
ஓகே. If I see the first question, find the Fourier transform 1 by square root of mod x here. But instead of Fourier transform, generally you can also expect like that here. Transform the function in the frequency domain. In that manner also you can transform function 1 by root x in the frequency domain. Frequency domain. It means that Fourier transform of this function. Fourier transform of this. This is a meaning, implicit meaning. Take first one, transform the function 1 by square root of mod x in the frequency domain. Uh, Next problem, second problem. Find the Fourier transform of f of x equal to. Find the Fourier transform of f of x equal to x 0 less than x less than 1 in the range 0 less than x less than 1. 2 minus x 1 less than x less than 2. 2 minus x 1 less than x less than 2. 0 for x greater than 2. Third problem, prove that the conjugate symmetry property, prove that the conjugate symmetry property f of minus x, Fourier transform of f of minus x equal to f of s whole bar equal to f of s whole bar. Equal to f of s whole bar. Solve for f of x here. Solve for f of x. You can also ask the question different manner here. Instead of solve for f of x, reconstruct. You can write like that also. Reconstruct the pulse f of x. Reconstruct the pulse f of x from the integral equation. From the integral equation. Integral 0 to infinity. Reconstruct the pulse f of x from the integral equation. Reconstruct the pulse f of x from the integral equation. The 0 to infinity f of x sin tx. Instead of sx here, I am using t, variable t. Instead of s, I am using the variable t. F of x sin tx dx. F of x sin tx dx. Instead of s, I am using the variable t. Here is also instead of s, t is present here. 1, 0 less than or equal to t less than 1. 0 less than or equal to t less than 1. 2, 1 less than or equal to t less than 2. 0 for t greater than or equal to 0 for t greater than or equal to 2. How can you proceed this problem here? Instead of yes, t is present, therefore you can change for our convenience, you can change integral 0 to infinity f of x one to 0, 0 less than or equal to t less than 1, 1 less than or equal to t less than 2, t greater than 2, t greater than or equal to 2. Therefore, for our convenience, I will change it as a variable s here. Integral 0 to infinity f of x sin sx dx. Instead of t, I use it as yes because that is the variable we studied so far. So it will be convenient for you. Like p, we change it as a n. There's also t, we change it as a yes. So it is like a Fourier sine transform definition. When if you multiply by root of 2 pi pi. If you multiply by root of 2 pi pi, it's similar to Fourier sine transform definition. Therefore, we multiply by root of 2 pi pi. Here root of 2 pi pi 0 less than or equal to s less than 1. Here 2 root of 2 pi pi 1 less than or equal to s less than or equal to 2. 0 for s greater than or equal to. Okay. So it is Fourier sine transform definition here. Therefore, what about the thing is given? We have fs of s. We have fs of s, this one. Fs of s is given. Question is that reconstruct the pulse f of x. Therefore, you are going to identify f of x from this equation. From this, if you want to identify f of x means you have to use inverse Fourier sine transform. Inverse Fourier sine transform is 0 to infinity fs of s sine sx ds. Sine. For 0 to infinity split it as 0 to 1, 1 to 2, 2 to infinity. 0 to 1 we have this value, 1 to 2 we have this value. Then integrate, you can get the answer. This is your f of x. In that manner we can proceed. Or multiply by root of 2 pi pi in the given equation. Also we change t by s for our convenience. You can get fs of s, you can get the answer. All of you understand here. Next problem is also the same and again solve for f of x, the integral equation, same idea, but it is cosine transform. Cosine transform. Cos s is this you multiply by root of 2 pi pi, you can get cosine transform. Solve for f of x, comma the integral equation. 0 to infinity f of x cos s dx. 1 minus s, 0 less than s less than 1, 0 is greater than 1. 0 is greater than 1. Okay. Next problem, find the Fourier cosine transform of 1 by x square plus a square. Find the Fourier cosine transform of 1 by x square plus a square. One by x square plus a square. Find f of x, seventh problem. Find f of x. If its Fourier sine transform is s by s square plus 1. If its Fourier sine transform is s by s square plus 1. Eighth problem, last one. Find FFST and FFCT. Find it Fourier sine transform and find it Fourier cosine transform. Sine and find it Fourier cosine transform. F of x equal to 3x for 0 less than x less than pi. F of x equal to 3x for 0 less than x less than pi. Okay, right. And also you see that for this type of problem, 1 by x square plus a square, s by square plus a plus 1, what type of idea we can follow means, what is the problem? Sixth problem, Fourier cosine transform of 1 by x square plus a square. Root of 2 pi pi integral 0 to infinity 1 by cos sx dx. Cos sx dx. The result will be a function of s. Result will be a function of s. But evaluation of this integral is somewhat tedious. Evaluation of this integral is somewhat tedious here. Therefore, for this type of problem, similarly, seventh problem also, they are asking f of x here. F of x from the s by Fourier sine transform, s by s square plus 1. Root of 2 pi pi 0 to infinity Fourier sine transform s by s square plus 1 sine sx dx ds. This integral, this part of integral also tedious. This part of these two parts are tedious. But anyway, the denominator is x square plus a square or s square plus a square. You have to remember one function. You have to always remember that if f of x is equal to e power minus ax, a greater than 0, then its Fourier cosine transform. Its Fourier cosine transform already we derived a by s square plus a square. Correspondingly, its Fourier sine transform is s by s square plus a square. S by s square plus a square. Okay. That will be the idea. That will be the idea. From this, you have the integral formula by inverse. E power ax can be written as root of 2 by pi integral 0 to infinity a by s square plus a square cos sx ds. Cos sx by inverse Fourier cosine transform, we can write like this. Yes, you see that here. This integral is also similar to this part again. Cos sx, but instead of s, x dx is present. Instead of x, s is there. Okay? Instead of s, x is there. What about your conclusion here? Here you have to get function of s. Your answer will be function of s. What about here? You are getting the answer. Answer is function of x. Or we change this same thing as a yes form here. But a instead of a here one is here. Therefore we take a is also outside here. Therefore definitely what about your answer for this problem will be means root of pi by 2. Well, root of pi by 2 e power minus ax by as by a. By considering comparing these two integrals, you can get instead of x yes, and a is also you take it left side. Well answer. Similarly, here for this problem also by inverse. What is inverse? Root of 2 by pi, integral 0 to infinity, s by s square plus a square sine sx ds. Inverse. Yes, here is also the same thing here, 0 to infinity s by s square plus 1. Instead of a 1 sin sx, s sin sx here. Now, what about your answer here from this? A is 1 here. Therefore, you can get your answer will be e power minus root of pi by 2 e power minus x. Because a is 1. A is 1. Therefore, you can get it as root of pi by 2 e power. For evaluation of this integral is somewhat tedious. Therefore, you have to remember this function. This function results are very much useful to evaluate this kind of integrals. This kind of therefore, already we know that we can start a statement that already we know that these things here. Therefore, the value of this integral equal to like this. Value of this integral equal to like this. Therefore, in that manner we can conclude. Otherwise, it will be very difficult to solve these integrals. I think all of you understand these ideas here. In that manner, we can proceed. Right. Okay. If you have any doubt, you can ask. That's all the session. I will create assignment portal. Depending on that, we can proceed. Submit. Thank you. Thank you for attending.